We will use rationalizing substitution to solve indefinite integrals. This is also a type of substitution method, with the main purpose of rationalizing the integrand so that the indefinite integral can be computed easily. This example involves computing the indefinite integral on the second line. To rationalize the integrand, we set u squared equals x. Differentiating both sides then yields 2u du equals dx. The second line on the screen shows the integral form after the variable substitution. The third line is merely simple algebraic manipulation to transform it into a simplified indefinite integral. The second to last line evaluates this indefinite integral, and the last line simply converts the variable u back into x. This example involves computing the indefinite integral on the second line. To rationalize the integrand, we will choose an appropriate variable substitution u. Since the integrand contains both a cube root and a square root, we take the least common multiple of 3 and 2, which is $6. Therefore, we set u to the sixth 6 equals x. Differentiating both sides yields 6 times u to the fifth du equals dx. The second line on the screen shows the integral form after the variable substitution. The third line cancels out u squared. The second to last line involves simple algebraic manipulation to transform it into a simplified indefinite integral. Next, evaluating the indefinite integral and converting the variable u back into x yields the results shown on the last line. This example involves computing the indefinite integral on the second line. To rationalize the integrand, we set u squared equals 1 minus e to the x. We need to solve for x so that we can differentiate both sides. Rearranging the terms gives 1 minus u squared equals e to the x. Next, taking the natural logarithm of both sides yields the expression on the second to last line. Differentiating both sides then leads to the mathematical expression on the last line. The second line on the screen shows the integral form after the variable substitution. The third line is merely simple algebraic manipulation to transform it into a simplified indefinite integral. The second to last line evaluates this indefinite integral, and the last line simply converts the variable u back into x. This screen illustrates how to convert a rational function involving sine and cosine functions into a rational function in terms of u. We will use the half-angle substitution. First, set u equals tangent of x over 2, as shown on line 2. On the third line, the first equality follows from the reciprocal relationship between the cosine and secant functions. The second equality is obtained using the identity secant squared x equals 1 plus tangent squared x. The final equality is reached simply by substituting u equals tangent of x over 2. The last line for the sine function uses the same transformation technique. The first equality there relies on a simple trigonometric property, and the last equality is again obtained by substituting u equals tangent of x over 2. Next, we can convert the sine and cosine functions into rational expressions in terms of u. The first equality on line 2 uses the half-angle identity for the sine function. By substituting the half-angle formulas derived on the previous page, we obtain a rational expression in u. Similarly, the first equality on line 4 applies the half-angle identity for the cosine function, and substituting the formulas from the previous page yields a rational expression in u. In addition, since we defined u equals tangent of x over 2, solving for x gives x equals 2 times arctangent u. Finally, differentiating both sides yields the mathematical expression on the last line. This example involves computing the indefinite integral of a rational function containing sine and cosine functions. First, set u equals tangent of x over 2, as shown on the third line. We can then substitute the rational expressions in u obtained previously. The calculation starts on line 4. On line 4, we substitute the rational expressions in terms of u for sine and cosine derived on the previous page. The last line is merely simple algebraic manipulation. The second line shows the indefinite integral after the variable substitution. By substituting dx and the rational expression of the integrand in terms of u obtained from the previous 2 pages, we obtain the indefinite integral of a rational function with respect to u on line 2. After simple algebraic simplification, we arrive at the indefinite integral shown on the last line. The second line rewrites the integrand into partial fractions that are easy to integrate. We split it into 2 fractional terms and then integrate them individually, as shown on the second to last line. The last line simply converts the variable u back into x after simplification.